My name is Lari Hotari. I'm a principal software engineer at StreamNative. I'm an Apache Pulsar committer and PMC member, and I've been contributing to open source for quite a while. And one fun fact is that I made my first contribution to open source by email in 2001. So some of our agenda today is first, since many might not be familiar to Apache Pulsar before, we'll quickly look over Apache Pulsar features so that you have some background on that. So please lift your hand up if you don't know Pulsar before. So Pulsar in 3 minutes. Apache Pulsar, it provides streaming and messaging in the same platform. So you get both the features that are you commonly see in, let's say, in Kafka, and then the message queuing feature is like, for example, popular platforms are like RabbitMQ. And so in Pulsar, you get these both. And one differentiator there is that Pulsar has these per message acknowledgments. So that enables these message queuing features. So message queues with Pulsar are in the form of a subscription, and one topic in Pulsar could have multiple subscriptions. And that's the entity which tracks acknowledgments, and essentially it forms a logical queue. And you could, on one topic, you could have multiple subscriptions, and these subscriptions could have, depending on the type, could have multiple consumers. So these subscription types are the ones that control this behavior. When the subscription type is exclusive, only a single consumer is allowed. And there you could do ordered message processing. And similarly with failover, you could do ordered message processing, but there you could have like a standby consumers waiting to connect. And the shared subscription is typically used as a job, like scheduling different jobs across multiple consumers, in which it distributes in a round-robin fashion. But that doesn't give you ordered processing. So for that, there's this key shared subscription in Pulsar where multiple consumers can be connected, and the messages with the same key, they will be always routed to the same consumer. So then a little bit more about these Pulsar features is that in Pulsar, there's 3 levels of elasticity that you could scale the consumers, scale the brokers, and scale the storage. And one of the key differentiators here is that when you want to go faster, you don't necessarily have to increase the number of partitions. So there's that's kind of like a big difference compared to Kafka. And then on the brokers, since they don't have persistent state, you could also scale those and add and remove brokers depending on the workload. And there's no data movement between the nodes because they don't have persistent state. And on the storage layer, there is a possibility to add more storage capacity, which is almost instantly available. And that's added by adding more bookie nodes to the cluster. And one mentionable feature or property of Pulsar, also in the storage area, is that by default, Pulsar's retention policy is such that the messages, the storage space is released after all the messages have been acknowledged in the subscriptions on a topic. So in that way, your intermediate topics, they don't have to retain the data for a fixed periods of time. So then finally into our actual subject of this talk is the key-ordered message processing and related challenges. And here we're going into these challenges in a fairly kind of like generic perspective and not specifically looking at it in the context of Pulsar, but in any key-ordered message processing, you have the category of these problems. So whether you use Pulsar or not, you benefit of these ideas. So in the key-ordered message processing, like first of all, like why are we doing this? Is that there's a requirement to process these messages or events in order, and the reason for that is that the processing in the incorrect order, that would have some negative impact on the system or the business domain. And it could be something that you end up in incorrect state in the system, and it would be like costly operations to reconcile the state back into a correct state. Or your customer service might be getting busy because angry customers are calling because of some problem that it has caused. So it could cause like systems to take incorrect actions as well. And in some cases, the business or the systems, they tolerate this in ordering to some extent. But typically there's some degradation of service of quality, or the quality of service. So the first challenge I'll be presenting to you is the scaling of processing. And that's the reason for this is that handling messages one by one, it will be too slow. Because if you want to do them in order, you have to handle them one by one. And the reason why we're talking about like key-ordered message processing is that the option to handle in parallel is to handle these keys in order and do them in parallel. And that's a way how to achieve higher throughput in processing. The second challenge is error handling. Since let's say if the message processing fails for some third party or downstream REST service that is temporarily failing, and you immediately send those messages into a dead letter queue, the result of that would be that you'd have a gap in your messages, and that's kind of like considered as violating the order of the messaging, because it would be hard to get those messages in the dead letter queue back into the correct order or somehow solve that problem later. Then one of the problems is key hotspots. Typically, it's common that business keys are unevenly distributed. Let's say if you use a customer ID or something as a key, there could be like some customers that are very large ones and some customers that are small ones. Like there's a long tail of very small customers. And this results in very unbalanced load in processing by key. And similar problem could exist also when the key cardinality of the currently active keys is too low. That you're simply, there's only a few keys that are active at the moment. So then a little bit of different problem is that this is from the IoT domain. This example is that you have a very high cardinality of keys. Let's say the device ID is a key, and you have a very high total throughput, but per each key, there's a very low throughput. Like let's say like one message per minute or one per hour, but the total volume is very high. And one of the kind of like secrets of Apache Pulsar and Apache Kafka high performance and high throughput is the use of batching. And in these cases, if one of the details in key ordered processing is that you cannot batch different keys into, or you have to kind of like batch always the same key into the same batch. And that results in the problem that you have very small batches or no batching at all. And the reason why this is kind of like a problem is that opportunity is missed in saving cost in batching. And there could be like 10x or 50x differences in how problems are solved in IoT systems. Then one challenge that is a little bit like kind of like outside of the broker's context completely, or at least it's at the boundary, is this exactly once processing. And in the case of the consumer receiving duplicate messages, from the consumer's perspective, it's also that you're kind of like receiving messages out of order, that let's say that you're at sequence 5 and you receive sequence 3, and which is kind of like a duplicate that came before, but it's kind of like out of order. And one of the important things to remember also here is that all consumer applications, they have to be implemented in an idempotent way. And transactions, they don't solve this in the case that your consumer application is doing side effects. Because let's say Kafka and Pulsar transactions, currently they are in the context of the messaging system. So they implement this exactly once in that context. And so typically there is some misconceptions around this at least once and in exactly once. So and one additional challenge, kind of like a little bit related to the previous one, this idempotency, is that there's this problem, distributed system problem, that in key-ordered message processing, you might need to be ensuring that a specific message or key is only being processed by a single consumer at a time. And this is out of scope of, for example, Pulsar consumer at the moment, that it doesn't have this type of leader election built on the consumer side where it could guarantee that you wouldn't be processing messages at the same time. And one example of this is that your network connection fails and the consumer application doesn't notice that the network is broken. But from the broker's perspective, it's broken, and it gives those messages already to another consumer to be processing. And then it ends up in the situation where two consumers are processing the same set of messages. So then I presented these challenges, and now we'll look into some of the practical solutions and recommendations to solve these. So for scaling up processing, like one of the common practices is just adding more topic partitions. And in this obviously, all these decisions come with trade-offs. And in Kafka, it has its own trade-offs where data has to be moved around and rebalanced and all this. And in Pulsar, there is parallelism for a single topic partition. And mainly, the enabler for this is that Pulsar has these per message acknowledgments. And the most well-known solution for this parallelism for a single topic partition is the Pulsar key shared subscription. But you could also do client-side parallel processing for a single topic partition or a key shared subscription, so that you'd be increasing the parallelism to a high number at the client side. So a little bit of the key shared subscription modes is that there's two modes. This auto split, which is one where you could add dynamically more consumers to the subscription without the need to reconfigure clients, and this is very useful in auto-scaling consumer applications. And the broker will repartition the hash range, and it'll ensure that messages with the same key, they're delivered and allowed to be in this unacknowledgement state to only one consumer at a time. And in the sticky case, each consumer specifies the fixed hash range, and here one of the downsides is that scaling consumers, it requires reconfiguring and restarting typically like most of the consumers, since you're changing assignments. And for these key hotspot challenge, some of the solutions are related to, like a simple solution is to use more fine-grained keys, like when that is available. Like let's say in the IoT domain that if the messages are using let's say a location as a key, well, there could be a problem that you cannot kind of like pick the device ID as a key, but then using a combination of those keys, like location in the device ID, or something like that where you'd have a more fine-grained key. And then one possible solution is to route these hotkeys to separate topics for processing, like in the case that you have a solution how to detect that, oh, these are the most important customers, that I'm going to route all the messages to this topic and have very performant consumers to process those messages, because I'm going to lose a lot of business if I don't serve those customers well. For the high-cardinality key challenge, here the goal is to increase the message batching. And one of the solution is to map these original keys to sharding keys. And obviously this solution adds a lot of like complexity and overhead itself, so it should be only used in these very high scale cases where you'd get a benefit of increasing the batching. And optimally, this reeking would be happening directly at the producers, so that there wouldn't be an intermediate step to first consume some other topic and then publish on another topic with a new key. And optimally, to get kind of like the most batching, and optimal sharding key cardinality would be about 10 to 20x of the maximum number of consumers required to handle the workload. So this number, I think I've originally read it from Akka documentation for Akka cluster sharding. But it's something that where consistent hashing works fairly well, that you have at least that many keys over that. And in the case of batching, when you have the least amount of keys, then that's how you get the most biggest batches in that case. So for key shared, some of the considerations is that it works out of the box for most use cases and supports auto-scaling of consumers. But in the case that like the strict ordering is extremely important, it's very important to solve these error handling, idempotency, and these concurrent processing challenges that's already covered in the initial design of the consumer application. And in some cases, it might result that it might be easier to solve these challenges by using, for example, the sticky consumer or using topic partitions. And I'll possibly explain a little bit later or in discussions. And then for this idempotency, that's something that has to be solved as well, like when this ordering is important. Since it's a reality that in distributed systems, you cannot get exactly once message delivery. So for reliable messaging, it's always at least once. And this results in that duplicate messages are expected. And one detail that sometimes causes a little bit of confusion is that Pulsar has a feature called message deduplication. And what that is about, it's for the idempotency for the producer side. So it's implementing the idempotent producers pattern. And that prevents the duplicates on the producing side so that they don't get stored as duplicates. And if you don't have that enabled, you'd already get duplicates stored in the storage. And in the case that your consumer isn't performing side effects beyond sending other Pulsar messages and acknowledging messages, in that case, you could achieve idempotency by using Pulsar transactions. But in the case that you have side effects, then you would have to consider like the way how you address that, whether to store it in your application database, having the state together with database transactions, or whatever the solution is most suitable for your use case. Then going into the scaling considerations on key shared is that typically many consuming applications are implemented in a way that it takes a message off the queue, and then it's going to call some REST APIs and then send some results to some other topics. And this doesn't really require a lot of like CPU power to do this. It's mainly I/O. And in these cases, it would be possible to increase the parallelism of a single Pulsar consumer to a very high level. It could be hundreds or thousands. And the way to implement this high parallelism in a Pulsar consumer, I'm now in the context of Pulsar Java API, is that you could simply increase the listener thread's value when you're using a message listener API. And then an improvement to this is that you could use the message listener API with Java virtual threads. So quite recently, this came possible by implementing a custom message listener executor. So this pip 359, it makes that possible. And hopefully we'll have a time to show a little bit of a code like how to implement this. Then there's the option to use the async receive API, but in that case, you'd have to implement the pipelining solution to keep the messages in order and process only one at a time, like in custom code. And then there is the Pulsar Reactive client, and Spring Pulsar Reactive. In that API supports this pipelining and configurable concurrency level for key-ordered message processing. So some of the alternative solutions for key shared autosplit is using exclusive or failover subscriptions and partition topics with high parallelism in each consumer to process the keys in parallel. And the reason why that's possible in Pulsar is that there's these per message acknowledgments, so it's very well fits in that solution. And one simple deployment solution for this could be that you have a Kubernetes stateful set where the partitions to consume are configured and selected by the pod index. So you have some application code that selects that, oh, when I'm this pod index 1, it's gonna consume partitions like 1, 2, 3, and then the pod 2 is gonna take 4, 5, 6, and so on. And it could calculate these directly based on the pod index. And a similar solution works also for sticky mode, where this could be done, that the hash range is calculated based on that. And then there's also like other options where you could have like actor framework handle all this stuff, but the downside of that is that it gets very complex. So then before the demo, I'll just mention these Pulsar key shared recent enhancements. So these actually came out already in Pulsar 4.0, the pip 379, where this the way how this repartitioning or kind of like rehashing happens is that there's this so-called like draining hashes solution that previously when new consumers joined or left, all the outstanding messages it would wait until those would be acknowledged before it would start sending like new messages to that consumer. And one of the other improvement in this this pip 379 is that for troubleshooting, you could use this stats endpoint to get visibility in this draining state. Like what are the hashes that are draining and what consumer is still pending the acknowledgement on those messages. Since it won't be sending the messages like after rehashing, it'll wait until all the messages on that for that hash has been acknowledged by the previous consumer that was consuming the messages, because otherwise the ordering would get mixed up. So in this case, there's some solution to that concurrent processing thing as long as that there's no network failures. So it prevents processing of the same keys at the same time in two different consumers. And then pip 430 came in Pulsar 4.1, and that's the Pulsar broker cache improvements. And the reason why that's related to key shared is that in the way how key shared works internally, it has to skip sending messages and put them into a so-called replay queue. And then when it's possible to send that to the consumer, before this change, it was very common that it had to actually go and read it from the bookie again, like the same message. And that would incur like network cost and also like unnecessary load on the bookies. So with this caching improvements, it's that solves it in many cases. And some of the future improvements that have been discussed for quite a while is this negative acknowledgement support for key shared. So that would be an improvement on this failure handling side, and then having notifications for key hash range changes. And that's something that is important in the case that a key gets assigned to another consumer, and then the previous consumer might have, let's say, a local cache, and it would like to remove those entries from the cache to save resources or something like that. One of the detail of this negative acknowledgement support is that most likely it would work in a way where when a message is negatively acknowledged, it would have some client-side solution to keep those on hold on the client side that have been already delivered to the client and are in the buffers. And then it would send a message to the broker that stop sending me more messages with this key. And there would be some back off that after some time, it would resume trying to process those messages, and then it would send the broker that you keep on sending me these messages if it succeeds on the ones that are already on the client side. So this solution is to avoid sending the messages into a dead letter queue, and so that they don't get into a mismatched order. And in the cases that a downstream service is temporarily down, it would be able to solve that issue. So then let's see if we have any time for a short presentation. Okay. So I'm not sure if the font is visible, but let me see if I. Can you see it, or should I go even? Let's see if presentation mode. Okay. So what I have here is the listener that is using this virtual threads executor. So I probably don't have time to demonstrate this, but I'll just show the implementation, like how it kind of like binds into the message listener API. So I created a test application where it's possible to set different parameters and tried out like this virtual threads executor, and it turned out to be a pretty good solution. And one thing that I want to thank Philip Dollef in the inspiration by his project where he demonstrated this with a lot of like different metrics around this. So this code is actually like very simple, that it takes a concurrency limit, which limits like how many tasks are being processed in parallel, so that you don't overwhelm that you have some control, because otherwise you'd be just taking as much as come to the consumer. And this is it has a concurrent hash map where there is the key is the message key, and for each key it has a virtual thread executor. And then simply it'll be using that to execute the message listener, and that's how it works. And it's fairly nice that since you could use the normal blocking Java APIs and get very high concurrency. Like I tried with the values like fairly high ones. Let's say, how are we on time? Like, do we have to end and take the Q&A, or? I'll do it in a 60-second demo. So one thing that I have is a simple HTTP server that'll do a delay of 50 milliseconds for each request. And the processing will be calling that. And then I have a generator to generate 1 million messages. And then I have the listener. And just to show the virtual threads with, obviously this won't be using this level of concurrency because there's, in the default parameters, I think I have 500 different keys, so it'll go up to that 500 in maximum, but just run it. Oh, I don't have the broker running, so that's. So now it's running here, and it's achieving around like 11 to 12,000 messages per second, and that's the handler itself is calling this backend that has fixed, or there's some jitter, but 50 milliseconds plus 10% jitter. So it's simulating REST backend. So it could run fairly quickly, even though that it's only running on a single consumer. So that was the demonstration, and let's take the questions. Yeah.
Broker failure handling, you said for the key shared that has a cache. What happens if the broker falls over or the cache, if it's in memory limit, is hit? Like, let's say my destination is a server that's down. I'm saving it to a database, and the database is down right now, for whatever reason. And then the queue is backing up with a bunch of these events. What happens with the broker? Is it using a cache that's external and saves it, or is it like an in-memory cache?
Do you mean the messages that are stored on the broker side?
Yeah.
So it's in Pulsar it uses Bookkeeper for the storage layer.
Okay.
So typically, like the broker cache that I was talking about, it's in memory, and there's certain memory limits that how much it keeps in cache.
Yeah.
So the messages themselves are immutable, so it's kind of like safe to cache it. So unless it's in the cache, it goes to the bookies. And then in bookies, there's a replication factor, like you could run with 2 or 3 typically. So if one bookie is down, it would go and read it from the other bookie. So that's how you get the high availability in that case. Any other questions?
So for implementing retry strategies, we have to wait for that pull request that you showed there for the negative acknowledgement on key share subscriptions in order to keep the order? Or is there any other way we can use today to avoid while you're sending, for instance, to the retry queue, right, associated to the topic when there's a failure?
Well, that's kind of like also in that case, it has certain limitations. So there will be certain constraints. So it is a fairly tricky problem to solve, like depending on the scale, because it works like that solution. Eventually, the message processing will stop, like because in the subscription, the acknowledgement state that has limits. In Pulsar 4.0, there's a limit now where you could specify when it stops reading ahead. And then if you're not processing the messages, eventually the state of the subscription is gonna hit that limit. So for more complex use cases, there has to be some strategy, like how to kind of like switch over the messages if it's not possible to stop.
Right. But in case that the customer is okay with stopping.
Yeah, in that case, I believe this solution would be a kind of like out-of-the-box solution for that. And obviously, like providing like feedback and requirements.